Frames are widely used in engineering practice around the world. Frame analysis is used to analyze simple frame. It is used to determine how the frame will act under external force. Shear and bending moment force can be found and may be shown in the shear and bending moment diagram. The structure is three-dimensional comparison of the floor slab, beam, column, and footing, which monolithically connected and act integrally to resist vertical load and lateral load. The analysis of a 3D frame considers the real behavior of the structure, but it is more complicated since the structure is highly indeterminate. In order to simplify the analysis, the 3D frame structure is generally divided into a series of independent, parallel, two-dimensional plane frames along the column line and longitudinal and transverse direction of the building.
There are three methods of analysis. First, one-level subframe. Second, two free-joint subframe. 3. Continuous and one free-joint subframe.
The moments and forces in certain individual beam may be found by considering a simplified subframe consisting only of that beam, the columns attached to the end of that beam, and the beams on the either side, if any. The column and beam ends removed from the beam under consideration may generally be assumed to be fixed unless the assumption of pin-ended is clearly more reasonable. The stiffness of the beams on the either side of the beam considered should be taken as half of their actual values if they are taken to be fixed at their outer ends. The frame analyzed will be subjected to different load cases. The load cases can be either max, which is 1.35 GK plus 1.5 QK, or minimum, which is 1.35 GK only.
To show how this method works, we are going to answer this question. The question is a frame with beam size 300 mm by 600 mm and column size 300 mm by 300 mm. Dimension of the frame is 7 meter long for the end beam and 4 meter for the middle beam. The upper column height is 3 meter and the lower column is 3.5 meter. The permanent load is 30 kN per meter while the variable 15 kN per meter. The shear force and bending moment of the beam and column are determined using two frame joint subframe.
For these load cases, we are divided by three sections, which is at the left and right section have two cases, which is for case 1 is maximum and case 2 is minimum. At the middle section have four cases, which is case 1 is maximum, minimum. Case 2, minimum, maximum. Case 3, maximum, maximum. Case 4, minimum, minimum.
So for this particular question, we will be dividing the frame into three different sections, which is the left, middle, and the right section, so that we can analyze two free joints of the section. So in this video, we will analyze the left section, so we can analyze joint A and joint B to determine the bending and shear force of beam AB. So in this section, there will only be two different load cases, which is the first case where it is maximum, and then case second, which is maximum, minimum. So the first thing that we have to do is to calculate the loadings of the beams. So in the first case, where both beams are subjected to maximum loadings, so the loads are 63 kilonewtons per meter for both beams. After that, we will be able to calculate the fixed end moment of both beams using the formula WL squared over 12, where W is the load, L is the length of the beam. So using that formula, we will be able to calculate the moment of beam AB, which is 257.12 kilonewtons meter, and beam BC, which is 84 kilonewtons meter. After we have calculated the fixed end moment, we can proceed to calculate the moment of inertia, I, for both beam and column using the formula BH cubed 12. So using this formula, we will be able to get these values. Next, we will calculate the stiffness K for both column and beam using the formula I over L, where I is the moment of inertia and L is the length of the member. So by using this formula, we can get the value for the upper and lower column, as well as the beams in this section. Next, we will have to calculate the distribution factor, F, for all the members in the joint that we will calculate. So the calculation of distribution factor involves the stiffness of the member divided by the sum of all members, stiffness of members in the joint. So, for example, the member AB, which is beam AB, will be divided with the sum of all members, sum of all stiffness of members in the joint, which is beam AB, the upper column and lower column. So using this formula, we will be able to get the distribution factor for AB, the upper column, as well as the lower column for joint A. For the next joint, there will be 4 different members, which is beam B to A, beam B to C, upper column, as well as lower column, using the same formula and same concept, where the member is divided by the sum of all stiffness member in the joint. So we will be able to get these values. So after we have done calculating the distribution factor, we can proceed to the moment distribution method. So in this method, we will tabulate our calculation as such, where the left table represents joint A and the right table represents joint B. The values highlighted in yellow are the distribution factors, and these are the values of fixed end moment that we have calculated earlier. So to use this method, we will have to find the actual moment at that joint. So for instance, at joint B, there are 2 values of fixed end moment, which is 257.12 as well as negative 84. So to find the actual moment at this joint, we'll have to add these 2 values together. So it'll be 257.12 plus the negative 84. So that value that we calculated, which will be a positive, we'll have to change its notation. If it's positive, it becomes negative. If it's negative, it becomes positive. So since the value that we calculated will be a positive, it'll be negative. So that value, that negative value, will be multiplied by the corresponding distribution factor of the member. So as such, we will get these values. So all these values are in negative. At joint A, there is only one value of fixed end moment, which is negative 257.12. So we will take this value directly, change its notation from negative to positive, and multiply by the distribution factor, the corresponding distribution factor. So we will get these values, all positive values. So next, we will proceed to the carryover step, where the joints, connected joints, will be carried over to the other. So for instance, joint A is connected to joint B by beam AB. Therefore, these values will be carried over to other side. For joint B, BC is not connected to any joint. Therefore, the carryover will proceed as 0. So these values, when it's carried over to the next, it will be halved, but the notations are kept. So if it's negative, it transfers to the other side as negative as well, but it's halved. So negative 70.98 will be negative 35.49. 167.13 will be divided by 2, which is 83.57. So now these values will become the total, the actual moment of that joint, and then we will repeat the previous step where the values will be changed its notation. If it's negative to positive, if it's positive it's negative, and then we will multiply it with the corresponding distribution factor. So we get all these values. We will repeat these steps until we achieved a value less than 1, and then we will sum all the values in the corresponding columns. So for instance, we will get these values for the lower column of joint A, this value for AB, and this value for the upper column. And the right table will be done the same. So we'll get these values. So these values represent the moments for the members at the joint. So next, we will proceed to calculating the second case, which is maximum minimum. So the beam BC will be a minimum load, which is 40.5. For beam AB, it will be the same, which is 63 kilonewtons per meter. After this, we can proceed to calculate the fixed end moment, the moment of inertia, the stiffness, as well as the distribution factor. But in this case, for the same section, these values are usually the same. They don't change. For the moment of inertia, the stiffness, and the distribution factor are usually the same. So after that, we will proceed to the moment distribution method, where it's practically the same as the first case. And the values of the moment will be recorded and then will be used to calculate the shear force. So example calculation of the shear force for we will have to calculate for both cases. So this is the first case where the moment of AB and BA will be taken because we will only be analyzing beam AB in this two joint method for this section. So moment at A will be 109.73 counterclockwise, and then moment at B is 246.25 clockwise. So, and then we will use the load which is 63 kilonewtons per meter at that beam. So these, this moment is for counterclockwise will be negative, and then the clockwise will be positive. So using this calculation, we will be able to identify the values of the reaction forces. So using this formula, we will be able to calculate the reaction force at A, which is 201 kilonewtons, and using the concept of equilibrium, we will be able to find the values of reaction force, the value of reaction force at B, which is 240 kilonewtons. And then we'll repeat the same step for case 2. So we will get the reaction force at A, which is 202.89 kilonewtons, reaction force at B, which is 238.11.
From the reaction that was obtained before, we will have to draw down our shear force diagram using obtained and given data. After that, interpolating of the shape's value acquires us the distance of crossing shear force line. To conduct bending moment diagram, we have to calculate area of each shape in shear force diagram. So don't forget to consider the moment of the starting point that was obtained using moment distribution method. So we will get this value. Repeat the action for both cases and get the full result of the action. So next, this is our result from middle section. As you can see, there are 4 lines involved that indicate the 4 cases in this beam. For the right section, it is like mirroring the left section as it have mirrored dimension and same value of loading. So this is the result.
As conclusion, we have successfully answered the question using two free joint subframe method and developed the envelope of SFD and BMD to determine the maximum of shear force and bending moment. Last but not least,
We have enhanced our knowledge in frame analysis. Thank you for watching and don't forget to subscribe us.
Please leave a like.